Hello, and welcome to another session on data mining. Today, we are going to talk about classification and how to build linear classifiers or linear discriminants by hand. So, we're not going to use any computers, we're going to just use our old school mathematics and some simple pencil and paper to make machine learning models. Okay, but before moving there, let me give you a brief recap of what we mean by classification. The objective of classification is to assign class labels or identify the type of an object. Let's say we had, in the first example, in the first lecture that we took, we had paintings by two different painters. So that was our unit of classification. So whatever goes into a classifier, that's a single example. Just to clarify the terminology, an example is a unit for which we want to generate a classification label. In this example on your screen, let's say we want to classify different types of fruits, then each fruit is going to be an example. We can extract features based on the sensor. So let's say if we are using a camera to capture the image of a fruit, and then we can extract features from that fruit. That would then become the representation of that particular example. That will go as input to a machine learning model, and we want to assign the type of that fruit, whether it's an apple, whether it's an orange, or a mango in this case. So, in case you're given a machine learning problem and you think that it's a problem in which you are asked to identify the type of an object. Let's say it can be fruits, just in this case, it can be paintings who painted a particular picture. It can also be, let's say, other classification examples, such as we want to identify the gender of a given person based on their mugshot or something. So all of those, if you are given a problem in which you are interested in identifying the type of an object, you can think of it in terms of classification. And once you start doing that, the next question you should ask yourself is, what is the unit of classification? What is the object that we want to classify? We will be calling that as an example. So an example in machine learning, again, means what we want to classify, what would be the input to the machine learning model, what would be the single input to the machine learning model. So in this case, we can extract features from a given picture of a fruit. Let's say we can extract features like redness, whether how much redness there is in the fruit or in the picture that we are given, how round is the object in a given picture. So let's say if we extract features from oranges, then we know that they are orange, so they're not probably red, and they are quite round, so that's why they score high on the y-axis. So all our oranges or orange examples are going to be represented in this scatter plot on your screen by these guys. So we can represent them like this. If you have a mango, mango have lower redness in comparison to oranges. That's why they are further left on the x-axis, and they're not that round. So that's why they score low on the roundness axis. That's why they end up over here at the bottom of this scatter plot. In terms of apples, apples are highly red. They are not as round as oranges sometimes, as you can see, especially these apples that you have on your screen. So you can represent them like this. Now, what we mean by designing a classifier is the following. We want to use this labeled data that is given to us. We have examples for which we know the labels, we know the true type of the object. So in this case, these four are oranges. We know that these four are mangoes, and these four are apples. We know their labels, and that is represented in this by the color. And we want to use this labeled information that's given to us to make a machine learning model, which is essentially a mathematical function that partitions this scatter plot or this feature space into distinct regions, each one of which corresponds to a certain class. So if you look at this particular picture, you see that there are this this trio of lines that you see over here. This one divides this party or partitions this feature space that is spanned by these two features called redness and roundness into three parts. There's a part over here that is essentially corresponds to apple land in this feature space. And then we have these mangoes and these oranges that have their own parts of the feature space dedicated to them. Then this black line that we made, and now I'm trying to color it over, is what will be called a classifier. So this is what we mean by a classifier. So it's a rule that allows us to divide the feature space into different parts. Just to go over some terminology, when we say training data, what that means is the data that has been given to us in which we know the features of a given example as well as the corresponding labels of that example. We use this set of label data called training data to determine what the function should be, what should be the classifier. So in this case, imagine this feature space that is at the bottom right of your screen without these black lines or without the classifier. So all we are given is a feature space in which we have these objects, and we can use this information or the way these objects span this feature space to make a rule that allows us to this this classify for this particular problem. This rule, the development of this rule is called training. Essentially, what we are doing is that we are trying to come up with a classifier. We are trying to find parameters. In this case, how should we, how should the lines look like that allow us to determine, allow us to classify, or allow us to divide this feature space into different parts. So that part is called training. As a consequence of training, you get these different, you get a classifier. Once you get a classifier, you can have a part of the training data, or you can have another data set in for which you know the labels, and you can use that to validate how accurate that particular classifier is. So that is called the validation data over here. Let's say we have got a few other pictures of oranges. So let's say if this is an orange represented by a star, and as you can see that this star is classified correctly, so it passes that validation step. We can have different apples that can be represented for which we know the labels. If they are classified correctly, we say that this classifier has passed the validation stage. In the real world, once we have developed a classifier and we have validated to give us an idea of how good or bad it is, then we go ahead and deploy it, and then the classifier is given real world examples for which we do not know the labels, we do not know their types, and then the classifier is used to assign types to these unknown objects. So that is what we mean by this test data part. So I hope this slide provides you a clear and concise explanation of what we mean when we say example. So an example in the machine learning is the unit of classification. You should know now what is meant by classification, and you should also know what we mean by a classifier. So next, what we are going to do is to develop a mathematical notation that allows us to reason about these classifiers and to develop these classifiers. So mathematically speaking, the objective of classification is to assign class labels. So let's say if you want to assign labels to pictures of fruits. So let's say if we got a picture like this one, then what we can do is we can assign labels or determine the type of this object. Let's say we have three different classes. We have mangoes, and we have apples, and we have oranges. So those are the three types of objects that we want to assign. So each example is going to be assigned one of these three labels. We can have a label set, which in this case corresponds to these three elements. It would have these three elements in this label set. So let's say C1 can be mangoes, C2 can be apples, and C3 it can be oranges. So in this case, this M over here is going to be 3 in our particular example. So the objective of classification is to assign each object that we are given as input, each example, one of the possible three labels, and we denote the output label typically by the variable y. Okay, so we want to assign these labels to a given feature vector, and we can represent each object as we've discussed previously. We can represent each object by extracting some features out of it. Let's say we use two features, and for this particular examples, we use two features called roundness and redness. So we can have two features. So in this case, each of these examples is going to be represented by a two-dimensional feature vector. So let's say for this particular orange, we can have quite it's quite red. It's not that red as an apple, but it's more red than mango. So let's say it has got a redness score of 1, and then it has a roundness score because it's pretty round. Let's say it has a roundness score of pretty high and 3. So we can represent this particular example of this particular orange as this feature vector. So in this case, this x is equal to 1 comma 3. We can sometimes write it like a column vector like this, and in this case the number of dimensions, or d, of this feature vector that is representing this example is 2, because we have two features. Similarly, if we talk about this apple over here, since it's quite red, so its corresponding feature representation can be it is pretty red, so we can uh, assign it a feature vector, a pretty high redness score of 3. And because it's not as round as an orange, let's say we can get a roundness score for this as 2. So again, each object of all the classes is going to be represented by a fixed dimensional feature space representation that we call the corresponding feature vector for a given example. In this case, in this simple example of fruit classification, or fruit image classification, I should say, we have used three classes and we have used two features. So each object is going to be represented in terms of these features. And once we have an object represented as a feature, then we are going to develop a classifier that allows us to predict what the label or the type of the given input example is going to be. Okay, so that is what we mean by classification. Mathematically speaking, the objective of classification is to assign a class label y from, so it's going to be exactly one of the following labels: oranges, mangoes, and apples, to a given feature space representation of an object or an example, which we typically denote with X. Okay, so I hope that formalizes mathematically what we mean by classification. So typically we have a number of training examples. Let's say we have about n training examples. So in this case, on your screens, we have 1, 2, 3, 4, 5 oranges. We have got 5 apples, and then we have got 10 mangoes. So the total number of examples given to us for training is n is equal to 10 plus 5 plus 5, which is equal to 20. So this n is then going to be 20. And each of these objects is represented by a two-dimensional feature representation. So D is going to be equal to 2. Typically, we denote each individual feature of a given example in the superscript. So let's say we can have an example. Let's call this example number 1. Let's call this example number 2, 3, 4, 5. Let's call this example number 6, 7, 8, and so on. So for example number 1, what we are going to say is that the feature vector of example, the first feature of example number 1 is going to be 1. Remember this one. And the second feature of this example is going to be equal to 3. So what we, in the subscript, we denote the identity of an example of a give from in the given training data, and in the superscript we indicate the feature that we have. So we have two features. The first feature in the superscript is going to be, let's say, the redness, and the second feature is going to be the roundness. So we represent that. So if you see x I comma j, then this j corresponds to the feature, whereas this I corresponds to the example. Okay, I hope that clarifies it. Over here, in terms of the notation, we can represent all the set of labels that we are given as a set. So we can have three labels for this example. So y is going to be equal to for each example, we've got a single label, whether it's, so example number 1, for example. So example means this machine learning example, let's say this one. Okay, its corresponding label that we know for the training data is going to be y1 is equal to, let's say, 1, and we can show that 1 indicates that it's an orange, whereas let's say y6 is going to be equal to 2, and that we know is an apple. Okay, so this is just going to be some mathematical notation. I hope it's clear. In the training set, we have n examples, and for each of the n examples, we know the corresponding labels, which are indicated by the corresponding values y. And the objective of classification is to find the magic function that allows us to map these input features onto those labels. So the objective of classification, if you put it mathematically, is then to design a function I'm going to call it F, that takes in X and then produces Y. Okay? So another way of thinking of this is you want F that allows us to map these d-dimensional features onto a single scalar, which is class label. Okay? That's pretty much that. In terms of the representation, evaluation, and optimization framework that we discussed in the previous lecture, let's frame this problem in that respect. So the first thing that we need to do when developing machine learning models is to define what an example is, and we've already done that. In this simple example, each picture of a given fruit is going to be an example, and then we are going to extract some features from it, which if we extract D features, then we can represent each given example by a D-dimensional feature vector. So that is the representation of the example in the feature space. Okay, so that part there. And then what we need to do is to define a classification function. Let's say if we use a simple line, if there are only two features, then we can use a simple line which is given by this equation. Anything above the line is going to, let's say, we are going to say that it belongs to one class, whereas anything that is below that particular line, we are going to say that it belongs to the other class. And then what the problem becomes is we want to find a line or we want to find a function that allows us to classify these objects correctly for the training data sets because we know the training labels in our data set. So we're going to use that in order to first define how much error a particular line is making, and then we are going to try to minimize that error in the optimization stage. Okay, so those are the three steps. First, we represent, we pick a function that we want to use as a classifier in this case. We evaluate how good or bad a given choice of the function is doing, and then we want to change the parameters in this function, which I've represented as W in this particular function that we have on your screen. We want to find those values of the parameters that allow us to reduce this error. So in this case, let's say if you want to compare it to the previous example that we had been following, if we were given a picture of a pathologist, that is going to go as input. We are going to extract some features, and then those features are going to go into a classifier, which is going to generate an output. And then we are going to compare the output of that machine learning model to the given training labels. So in this case, if it's a pathologist and the output of the machine learning model is also a pathologist, then there is no error, so we don't need to change this classifier. But if there is an error on the training data set, then we would go ahead and change the parameters of this classifier. We would change this classifier until we are satisfied that it produces good errors or a good or small amount of error over the training data set. Once we are satisfied with that, we can go ahead and test it either over a validation data set, and then we can put that into practice. However, as machine learning designers and as data scientists, one thing you must realize is that getting 100% accuracy over the training set is no guarantee that that particular machine learning model is going to generalize over an unseen test set. So the true test of a machine learning model or the effectiveness of a machine learning model is how well it performs an unseen test data or how good is its generalization. Okay. Moving further, what we are going to talk about is a very specific way of developing classifiers, which is called discriminant based, which is sorry for the horrible line that I just drew on your screen. Uh, it's called discriminant based classification. So I hope you are able to follow that. So in this type of classification, let's say if you have C different classes, or if you have M different classes, M can be three in our example of fruit classification, we have mangoes, apples, and oranges, then the objective of classification is to design or develop a function, or in this case, three different functions, so that the first function determines whether an object is an apple or not. The second function can tell us whether that particular object is a given object that is given as input to this function is an orange or not. And the third function can tell us whether it's a mango or not. And we can determine, let's say if we got these three functions, I'm going to call them F1, F2, and F3, corresponding to whether this is a mango, an orange, or an apple, then at time of classification, what I'm going to do is I'm going to give the feature representation that I have for a given object to each one of these functions. Ideally, a given function, let's say f1, should produce a high value at its output whenever the input object is a mango. It should produce a low value otherwise. Similarly, if we have f2 and the input we give it is actually an orange, then f2 should generate a high value at its output. And then we have the third function, which is corresponds to an apple. If we give that an apple as an input, it should produce a high value for an apple and low value and otherwise. We can, if we somehow by magic, if we are able to identify, we are able to build these functions, then what we can do is for a given object, we can pass it to all three of them, and we can determine the class of the given object by determining which of these functions is giving us the highest score. So this is mathematically put in the following way. So in this type of classification, the objective is to learn a function, or in the case of more than two classes, a set of functions. As we've done, we have three functions for our particular example from the training data set. So these functions will be learned, and by learning we mean we'll determine these functions based on the training data that we have, and these functions can then generate decisions for test data such that the classes in the data can be separated. So we can assign the class label of a given object. Let's say if this is a given object X, so we represent it by its feature representation X. We can determine its class by determining which of these functions, which of these three functions is giving us the highest score. Let's say you have got a single feature representation of a given object and we put it into X. First, we give it to F1, and let's say that produces a score of 0.2 at the output. Then we give it to F2, and that produces a score of zero point 0.1. And when we give it to F3, let's say that gives us a score of 0.9. Okay, and out of these three, which of them is the largest? F3 is producing the largest output. That's why we are going to assign the label 3, or in this case, which corresponds to an apple, to this object. So most probably the object that we are given as input to these three functions is uh, going to be an apple, and that's how we perform classification. If you are trying to build a mental picture of this, then you can think of these three functions in this case in the following way. So fk of x, that is a particular function fk, tells us what is the degree of belief that this object that is given as input x is it belongs to class K. So it tells you the K classiness of an example. So this is an unofficial term, but what it essentially means is what is the degree of belief that this example X belongs to the class K. We have three classes in this case, and in this example that I just put in front of you over here on the right part of your screen, we can say that for this example, since the largest output came from F3, therefore that given example is going to be most probably an apple. So this way of developing a machine learning model for classification is called discriminant-based classification. And we have got a function, a single function called C of x, that essentially partitions the feature space into three parts in the case of our example, such that we have three different functions that score high in a given region of the feature space. Okay. If there are only two objects, then you don't need to have a separate function for each of the two classes. So if you have, let's say, uh, a binary classification problem, let's say we have two artists only, or if you have two types of fruits, then you don't need three functions. You just need a single function. If that function value is greater than 0, then you are going to say that the object belongs to the positive class, and if that value is less than 0, then that object belongs to the negative class. So I leave that to you to figure out. It's a pretty straightforward explanation that is given on your screen, but I'm going to leave that to you to understand this trivial construction. Okay, let's take another example. So this is a binary classification problem. Uh, which has been represented in terms of two features. Let's say we want to classify the gender of a person based on their height and given weight. So we represent each person by their height and weight on this feature space plot, and such that one gender is indicated by diamonds, by red diamonds, whereas the other one is indicated by these blue circles. So this is a binary classification problem because it has two classes, and let me change the color of this. So, and we can build different classifiers. We can partition this feature space by different means. We can use a line like this one, and then that divides the two parts, this particular feature space into two parts. And this such a classifier which is a linear function is called, of course, a linear classifier. We can also have nonlinear classifiers that produce a nonlinear boundary. So let me draw, let's say if we have got a function like this that I'm showing uh, with the green line on your screens. Let's say if we got a function like this that partitions this feature space into two parts. One part of the feature space lies within the function, which essentially corresponds to all the blue points. And then there's a part that falls outside of this function, okay? And that part corresponds to these red class or the diamond class in this case, okay? So this classifier that you see that I've just drawn is a nonlinear classifier because it is a nonlinear function. It has a nonlinear discriminant. It's not a straight line, unlike this orange classifier. Now, one of the questions I want to ask you is the following. Which of these classifiers is better over the training data set? So I'm going to pause here and you can think of this question. I think most of you would have come to the correct conclusion that the nonlinear classifier does a better job over the training data set because it has neatly divided this feature space into two parts. At a high level, all machine learning methods partition the feature space based on in a meaningful way. So in this case, we had two functions, the orange function, which is a line, and the green function, which is a nonlinear classifier. Over the training data set, we do have some misclassifications from the orange line. And let me change the color to orange, please. Okay. So we can see that this particular example over here is misclassified by this line. So everything above this line on this side should have been blue class, whereas everything on this side of the line should have been red. But this is not the case for this particular example, or for this particular example, or for this example. So it produces three errors. It misclassifies these three examples. On the other hand, if we take a look at this green line, let me change the color again, please, we see that it correctly classifies all of these training examples. Okay, so if you measure the error that this orange line produces over the training data set, then that linear classifier produces an error of three misclassifications, whereas the green nonlinear classifier that I've just made in front of you does zero error. So over the training data set, we can say that this classifier, the green classifier, is a much better classifier in comparison to that orange classifier. One type of nonlinear classifier that we have posted some resources for that on the course page is a very simple classifier called k-nearest neighbor classifier. So what it does is that it assigns the class label of to a given example based on where that example lies and what is the majority class within its neighborhood. Let's say if we have this particular feature space that is shown on your screen, okay, over here, and I give you an example. If there is an example over here, okay, the one that I'm trying to represent with a green circle over here, then since in this case its nearest neighbor is a red one, is a red class example, so this probably is also going to belong to this red class. So that is called one nearest neighbor classifier. or simply the nearest neighbor classifier. So it assigns labels based on what is the closest example of a given example at test time. So we use that information to assign labels. If we can also increase the value of k to say, let's say 3 examples. So if on the basis of that, if we use k is equal to 3, then we first determine the 3 nearest neighbor of a given example. This is the first nearest neighbor, then this can be the second nearest neighbor, and then this case, this over here is going to be the third nearest neighbor. Since 2 of these nearest neighbors belong to the blue class, whereas only one of these nearest neighbor belongs to the red class, so the majority of neighbors of this green example are blue. Therefore, this particular example can be classified as a blue example. Now, if you follow this rule, then this example over here for k is equal to 3 is going to be classified as blue. Okay. If we use k is equal to 1, then it was being classified as red. So we can determine a boundary of these examples based on this rule. So since this is going to be red, this example I asked that as a question to you. If you use k is equal to 1, then what is your opinion? What is this example going to be classified as? And I'm going to pause here. Since the nearest neighbor is red, therefore this example is also going to be classified as red. Whereas this example that I've just drawn on your screen, since its nearest neighbor is going to be blue, so this is going to be classified as a blue example. If you use that rule and if you think about it, then you can think that different points in this feature space are getting colors assigned to them based on who their nearest neighbors are. If it's in a primarily blue neighborhood, we are going to classify a given example as blue. Otherwise, it's going to be red. And that allows us to partition this feature space into different parts or into different classes. And that's how a k is equal to 3 nearest neighbor example works. So what I'm going to do next is going to show you a demo of this thing in action. Let me switch back to uh, yeah, I can access this. Yeah, here it is. So this is a demo. The link of this demo for k nearest neighbor classification. We'll post a link on the course page. You can access it using that. This is an excellent resource to understand how k nearest neighbor works. Let's say we want to just do binary classification. So we have only 2 classes, and we let's say have 60 different points. Now, if I have this particular data distribution, we have 2 features. Remember, this is one feature, and this is along the y-axis is the other feature. We only have 2 features. We extract, that means we represent each given example in 2 dimensions. We have 2 different classes. I'm going to call one of the class blue class, and these are examples of the blue class. And on the right-hand side, you can see some examples of the red class. If I use k is equal to 1, then the example where my cursor is right now, if there were an example there, because the nearest neighbor of that particular example, yeah, so I hope you can see my cursor over here. And if you see that, then you can easily understand that the nearest neighbor of that example is the red one. So this region is going to be, this particular point is going to be classified as red. And this is a strategy that has been used to color this feature space. And as you can see, all this big region that you see as red or pink belongs to this red class. So if you have a set of training examples for which you know the label, then this is the classification boundary that is generated, or this is a discriminant function that is generated by this particular type of classifier. And as you can see, it's not a straight line. If it were a linear classifier, what we would see is a straight line, but it's not a straight line. It's slightly curved. Okay. So this is a nonlinear classifier. So if you go into an interview and someone asks you, is k nearest neighbor or is k is equal to 1 nearest neighbor a linear classifier or nonlinear classifier? I think you should know the answer to that by now. Okay, so if I move, let's say this data point over here, you can see that the boundary changes. Okay, and we can move a point over here, and as you can see, even a single point can change the boundary of this, the classification boundary for this particular classifier. So we can move different points around and we can get different classification boundaries. Okay. We can increase the value of k. Typically, we increase the value of k to be odd numbers because otherwise we can, if we set k is equal to 2, for example, then at a given point in the feature space, one point can be, one nearest neighbor of that point can be in the blue class and the other one can be in the red class. So we'll not be able to make a decision. So typically we choose odd values of the nearest neighbor. And in this case, if I choose k is equal to 3, as you can see, the boundary changes from 1 to 3. And I asked you the following question. Which of the two boundaries is smoother? The one corresponding to k is equal to 1 or the boundary corresponding to k is equal to 3? So I'm going to pause here to give you a moment to think. Okay, I think you would have arrived at the correct conclusion that the k is equal to 3 boundary seems a bit smoother than k is equal to 1. And by smoother means you can see that this is quite irregular because this boundary, when we have k is equal to 1, changes very easily because it's based on a single nearest neighbor. So all points where my cursor is right now belong to the red region because of the existing of this single point in the training data set. If you take a look at this blue point, then what you see is that this particular blue point allows all the points within its nearest neighborhood to be classified as blue. Whereas when you increase this value of k, then the rule that we are applying is the following. So for a point over here, we determine what the nearest neighbors, what is the number of nearest neighbors of a particular class at this point in the neighborhood. And that is going to be blue because there's only a single red point here. So as you increase the value of k, the boundary is going to become more and more smooth. Okay. So, so the most irregular boundary is produced by the k nearest neighbor classifier when k is equal to 1 and so on. Okay, so I hope this demo illustrates to you the concept of, first of all, what is a nonlinear classifier, and I hope you understand it enough to know how a k nearest neighbor classifier works. Okay, so what we have covered so far is we have covered the mathematical notation that we are going to use for solving classification problems. We are given a single example, which is then a mathematical representation or an abstraction of a given object in the real world. So we represent it by a certain number of features. That number of features can be d. So in the example that we took, there were two features. In this particular example on your screen, it's still the number of features is equal to 2. And one of the biggest reasons for that is because having two features allows us to visualize these data points. If there were like 3 dimensions, we could still visualize them in a 3-dimensional scatter plot. But as the number of features increase, it would become more and more difficult for us to be able to visualize that. So we represent each example in a feature space. Then what we do is we pick a function that we want to use as a discriminant. So in case of binary classification, we only need to pick one function such that if that function produces a score greater than 0, then we say that every point that produces a score of greater than 0 from that function belongs to one class. And if that function produces a value of less than 0, then for a given example, then that example belongs to the other class. Okay. But for more than two classes, you can have we can have the number of discriminant functions equal to the number of classes we want. Let's say if you have 3 classes, then we can have 3 different discriminant functions that we can combine to assign labels to a given object based on the formula that I showed you on the previous slide. Let me go back there so I can relate that to you. So this is the function that allows us to combine these 3. So if we have 3 functions, then we simply say whichever of them is producing the maximum score, we are going to use that function to identify what class that particular example belongs to. So if you're not familiar with this argmax notation, let me switch to the pen. Let's say we have these 3 functions, f1 and f2 and f3. If we want to determine which of these functions is producing the largest value, then we can use this argmax notation. What that means is assign the class label for a given object x to be equal to whatever identity function, whatever function in this case K can be 1, K can be 2, or K can be 3, produces the largest score. And for the example on your screen, we noticed that we got the largest value for our fictitious example from K is equal to 3, therefore C of X is going to be 3. Okay, it's not going to be zero point 0.9. The difference between argmax and max is the following. Let's say we have three values. We have a zero point 0.2, zero point 0.1, and zero point 0.9. Now the max of these is of course zero point 0.9, but the argmax of these is going to be corresponding to the index at which that value occurs. So if you take this as index 1, this as index 2, and this as index 3, which we have done in the case of these functions, then what we are going to get at the output of this argmax is this 3. So that's how we assign this class label. So up till now, we have defined and represented these discriminant functions. And next, what we are going to talk about is what is linear separability, which is one of the most important concepts in data science and in machine learning. Okay. So before moving on, before I forget, we also discussed what's the difference between linear and nonlinear classifiers. So a linear classifier is a classifier that separates or partitions the feature space using a linear function. So everything above the linear function is going to be one class, and everything below that is going to be the other class. And then we also talked about nonlinear classification boundaries, which are, of course, as the name says, nonlinear. So on your screen is an example of a nonlinear classification boundary. In general, k nearest neighbor classifiers, or especially nearest neighbor classifiers, are always going to be nonlinear because they generate nonlinear classification boundaries. Okay, this brings us very nicely to the next concept that we want to discuss, and that is linear separability. It's absolutely critical that you understand this concept before we move on to more complex models. So, linear separability is a very simple concept to understand. If you're given a training data set, let's say if you're given this training data set that's shown on your screen, it has these two features that you can see, one feature on the x-axis and the other feature on the y-axis. What do you think? Can this data set be separated into two parts, or can we partition this feature space so that one part of the feature space contains objects of only one class and the other part contains objects of only the other class? So I'm going to pause here and give you a moment to reflect on this. So in this particular example, as you may have noticed, is that it is not possible to have a single function or a single line so that everything above the line is going to be one class and everything below the line is going to be another class because of this single example. So what we would say is that this particular data set is not linearly separable. If this example was not here, this particular blue example, if it were not there, then we would say that this particular data set is linearly separable. Or we can use a linear classifier to classify it with 0% error over the training data set. So the definition of linear separability is the following. If data points in a given data set can be separated by a linear discriminant, then that data set or classification problem is called linearly separable. Now we are going to define it in a bit more mathematical manner. So all of us who are familiar with the equation of a line, we in our high school or later, we have seen equations like this. Y is equal to mx plus c. So if we plot that, we take x on the x-axis and we take y on the y-axis. And if let's say m is equal to 1 and c is equal to 0, then what we end up is a line like this one. If we take m is equal to, let's say, 2 and c is equal to 0, then we would probably end up with a line that has double the slope of the first line and so on. So we are all familiar with the concepts of lines. What we are going to do is to build on top of that and represent it in we are going to represent this simple equation in a different manner. Remember, we use the variable y in machine learning to indicate the label or the type of a given object, and x is used to indicate a vector that contains different features for that object. So we'll need to make a change of variables. In general, you can represent a linear function in the following way, as is done over on your screen. A linear function of variable x with parameters w is a linear combination of w, of these what we call weight values, and these features that are given as input. So let's say if we have an example x that is represented by these d features, we have x1, we have x2, and then we have these d different features, then this is a single example. We represent that as a vector. For that particular example, if you want to define a function over this feature space, that is of which x is a part, then we can do that by using the following equation. Okay, the equation that is I'm trying to highlight on your screen. So w1 x1 plus w2 x2 plus up to so on wd xt plus b is equal to 0. So b is called the bias term, whereas these w's are called weights of the linear function. So there are d different weights corresponding to d different features, and then we've got a bias. So as you can see, this is a product. This is a sum of products. So we have a summation. First we do a product, and there's another product. Then we have another product, and we sum it. So we have got a summation of products over here, and then we add a bias term b is equal to 0. Now, this is quite different from the seemingly quite different from what we have over here, the feature representation or the representation of the line that we are more familiar with, or you may be more familiar with. But if you think about it, there's a direct corresponding between this line, this representation of the line, and this representation of the line. If we take, in this example, in this case, if we assign y is equal to minus of x2, and I know this minus doesn't seem uh, very intuitive right now, but it will be in just a moment. And if we take x is equal to x1, and if I take m is equal to w1 by w2, then if you put all of this in this equation, then that means minus x2 is equal to W1 over W2 plus C. And if you multiply this, sorry, this should be an X1 here as well, right? And if you multiply this, then this becomes minus W2 X2 is equal to W1 X1 plus C times W2. So if we rearrange this, then that becomes W1 X1 plus W2 X2 plus CW2 is equal to 0. And if we replace CW2 by B, then we end up with this equation W1 X1 plus W2 X2 plus B, okay, is equal to 0. So the point I'm trying to make over here is that this representation that is a bit more, seems a bit more complex, is actually no more or no different from the equation of the line that you are quite familiar with. It's just a change of the variables that we have done. Okay, and the good thing about this particular function or this line that we have drawn over here, or the representation, this generic representation over here on your screen, is that it can be extended to multiple dimensions, not just two. So let's say if you have more than two features, you can still use this representation of the line. So I hope that now you would be familiar with what this representation or this function means. It's simply a line. If it's in 2D, it's a line. If it's in 3D, it's a plane. If it's in 4D, then this equation becomes a hyperplane and so on. Okay? And the definition of linear separability is the following. If you are given a data set in a certain dimensional feature space, and if you can separate it by using a linear discriminant, like the one that you have on your screen, then we say that that data set is linearly separable. Or in more precise words, if we have a linear function like this one, if we can find such a linear function like this one, such that for all the points of one class, let's say the positive class for which the label is +1, all this function produces a value greater than 0, and for all points for which the given label is -1, then all those points are below the line, or f of x for those points is less than 0. So You can think of it in geometrically. If you're having trouble with understanding it algebraically, then you can have an intuitive understanding of it in terms of geometry. So on your screen is the geometric representation. If we are able to find a line that separates the two classes in the given training set, we were not able to do this for this particular data set that is on your screen because there was a single point that doesn't allow it. But if we were able to do that, then we would say that this particular data set is linearly separable. Mathematically, what that means is that if we are able to find specific values of W1, W2, and up to so on to WD, and the bias parameter B, then we have essentially found a line that separates the two classes. Okay, so we are going to try to do that for a bunch of examples in this lecture. On your screens now is a classification problem that we started off with. It's the pathologist versus computer scientists classification problem. All the pathologists are colored in green, so we call them the green class, and we are going to give them the classification label of +1. Okay, and then we are going to give the classification label of -1 to all computer scientists, which are represented by these red rectangles that you see on your screen. My question to you is, in this particular feature space, so there are two features, and each point is being represented by these two values. Can you find a line that separates these two classes?